In this video, we are going to discuss differentiation from first principles, or the Newtonian method of differentiation. So, the differential of a function is denoted by f prime of x, and it's given by f of x plus h minus f of x all over h. And well, I forgot to put in something here, which was the limit as h approaches 0 of f of x plus h minus f of x all over h. Now this here is the definition of the differential from first principles, or the Newtonian definition of the differential. Let's see this in action. So, given the function f of x equals to 3x plus 5, let's use this formula. So, currently working up here, we say the limit as h approaches 0 of f of x plus h minus, well, f of x was just 3x plus 5 all over h. Now this f of x plus h part simply says wherever you see x in the function f, you substitute x plus h. It's like substitution in normal functions. So we go 3 of the x there, x plus h minus 3x plus 5. Put this in brackets all over each. Now we expand, put the imply, we get the limit as h tends to 0 of 3x plus 3h minus 3x minus 5 all over h. Now taking the working up here again, you have the limit as h approaches 0 of 3x all over h plus 3h all over h minus 3x all over h minus 5 all over h. Now this and this would cancel, leaving the limit as h approaches 0 of 3h all over h minus 5 all over h. Now this would cancel, leaving the limit as h approaches 0 of 3 minus 5 all over 0. Direct substitution, this would just 0 out, and you would end up with the differential of the function being 3, which if we use normal differential, this would have just been 3. That other method of differentiation where you minus 1 from the power and multiply by the original power. It's called Leibniz differentiation. This is Newtonian differentiation or differentiation from first principles. Let's go over our next example. Let's do another example of differentiation from first principles using the Newtonian method. So given the function 3x squared plus 4x minus 2, using the normal power law or the Leibniz method, we know the differential would be 6x plus 4. So from first principles, the differential is defined as the limit as each approaches 0 of f of x plus h minus f of x all over h. So we have the limit as h approaches 0. Now wherever we see x in the function f of x, we put x plus h for the f of x plus h part of the formula. So we say 3x plus h all squared plus 4x plus h minus 2. Now minus 3x squared plus 4x minus 2 all over h. So we have the limit as h approaches 0. Expanding this x plus h all squared. Just recall a plus b all squared is equals to a squared plus 2ab plus b squared. So we would get 3x squared plus 2xh plus h squared plus 4x plus 4h minus 2 minus 3x squared minus 4x plus 2 all over h. Let's expand this 3 into this quadratic. So we will have the limit as h approaches 0 of 3x squared plus 6xh plus 3h squared plus 4x plus 4h minus 2 minus 3x squared minus 4x plus 2 all over h. Now look carefully, this would cancel, 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 this would cancel. So we would remain currently working here with the limit as h approaches 0 of 6xh plus 3h squared plus 4h all over h, which is the limit as h approaches 0 of 6xh all over h plus 3h squared all over h plus 4h over h. Cancel, 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 h, cancel, cancel. We would remain now with the limit as h approaches 0 of 6x plus 3h plus 4. Direct substitution would just yield the differential to be, meaning when I substitute h as 0 into this above equation here, we just end up with the differential being 6x plus 4, which is what we would expect from the Leibniz method, or minus n1 from the power and multiplying it by the original power. That would be discussed in later videos.